Right, we look at Chapter 8 problem sheet, and I have model answers for that for this chapter. Let me just look at the first question. First question is a very straightforward question. You have been given a second order band pass filter. You can see that is a second order band pass filter, and you have got S here on the top, so therefore it has to be band pass. All you've been asked is apply bilinear transformation to the equation. So you are applying directly. You are not looking at any pre-warping or anything here in this question, because nothing, you were just asked to apply. So B is the bandwidth of the band pass filter. So you know the band pass filter is something like that. It will have a center frequency, and you go from the top 3 dB down normally, and that's the distance, that's called the bandwidth. Yeah. And that's the bandwidth, and omega p is the center frequency, which is like that position roughly is the omega p. So all we are going to do is that we are going to substitute for S our bilinear transformation. So this is our thing, and we are going to substitute for S in a bilinear transformation is 2 over t times 1 minus z to the minus 1 over 1 plus z to the minus 1. So you directly substitute that for S. So for this S, we substitute this one, and then this is for S squared. This is BP times S. And then you do the simplification, which you can do. This is just simple algebra. When you finish the simplification, you get this equation. And we normally want to make sure this is 1. So you divide everything by with that number. So when you do that, it will be in this format. So we've got, this is your A naught, which is here, and which is same as A1 as well, because we are multiplying inside, so the same A1. And then this coefficient, this one, which is we call is the B1, is going to be that much divided by that, which is here, and then B2 is going to be that one divided by that one, which is here. That's all the first part of the proof is. So there's no manipulation, nothing, just to directly substitute. So the frequency response will be warped here, but we are not doing any pre-warping. You are not asked to do anything. So you are asked to prove this. So direct substitution. And the next part is the one which actually looks at pre-warping. So a digital filter with a center frequency of 1000 Hertz, bandwidth of 150 Hertz. So it's center frequency of 1000 Hertz, that's 1000, and the bandwidth of 100 Hertz, that's 100 Hertz. Now we've got to implement this one. And now you've got to make sure you're going to get digital filter now. And what you need to do, we have to do warping here. So you've been given the bandwidth. This is the center frequency, which is 2 pi times 1000. Then bandwidth is 2 pi times 150. You can, in reality, you need to find theta p here. And instead of that, what we do, you can do that here. No, there's no problem. Theta p is equal to omega p times of sampling frequency. And here is BP, so we don't call this as theta p, we might call it as capital BP, which is equal to BP times T. It's like a theta, it's in radians per second. We could do that first, but other way of doing it is we want to find the analog frequency, warped frequency. Now this is the theta part. So we say the warped frequency is going to be 2 over t tan, so omega p is equal to omega p as 2 over t tan theta p over 2. That's what it is. We can rewrite this as 2 over t tan 2 pi omega p over 2. We can do that way as well, right? So that's what we have done here. We just say that first is equal to omega p theta is omega, omega pt. This is, beg your pardon, that's omega pt. So, which is omega p t over 2. So you substitute the values, it's given to you, and you substitute the value accordingly. You get tan 2 pi that's 10 to the minus 4 is your sampling frequency was given, 10 kilohertz, so it's T is 10 to the minus 4. You get that's your pre-warped frequency. Now for bandwidth also you have to do the same, so you go 2 over T times 10, 300 pi, which is 150 is what was given, is you can say 2 pi and 2 pi f, so that's 300, 2 pi f is 300 times 150 is 300, and T over 2 then, using this formula. So this is equal to, if you want to say 2 over T, tan T over 2 times 2 pi f, really, that's what it is. That's what we are substituting there, and you get 943 radians per second. You've done all the warping. Now you go back to the previous part. You need to get this value first calculated for the coefficients. So you go and then say, right, we are going to calculate that. You substitute all your pre-warp frequency, that one, and you calculate, and you substitute that one, you get that value. Now you go A naught and A1, so you go back, A naught and A1 is equal to 2 times the BPT divided by that. So you go back again in your thing, 2 times the BPT, that's there, divided by this number, you get that coefficient. Similarly for B1 you do that, and also B2 you do this 2 coefficient, then you substitute them back in your transfer function. This is another way of doing the digital filter calculation. So you can do, this is an alternative way of doing it, and there are other ways of calculating as well without substituting. You pre-warp first and then substitute as well, but this is fine. Now in the same question you are asked, this filter that you found, is that a stable filter? So we can do 2 ways. One is the stability triangle. Remember stability triangle we learned, which is we plot against B2 coefficients and a B1 coefficient. And if the poles are inside here, if the coefficients are inside, if you plot this one, if anything is in here, the point, then it's a stable one. So in our case, B2 is 0.918, so it will be somewhere here. Well, not minus 1.55, so therefore minus 1 is there, minus 1.5 there, 9 is there. So it looks like it's going to be in here, the point. So it should be stable. But sometimes very difficult to know when you plot it, unless you plot them right. So instead of that, what you could do is you find the poles of that. Using MATLAB you can find the poles, and if you do that, so you just select only the pole part of it, so 1 over that, all pole, and find the poles of that, and that works out to be, the poles are inside the unit circle, therefore it's a stable system. So you can do both ways. Here is very clear, if it is less than 1, if the coefficient is less than 1, it will be definitely going to be inside unless above 1. But when it's greater than 1, you're not 100% sure, so you really need to work out the value. You can actually work out whether that point is this side of the line or this side of the line. There's a mathematical technique you can use to find out, or easy ways to find out this one. So it's a stable system here. Okay. Let's move on to the question number 2. In this case, impulse response of a band pass filter is given. So what's the band pass filter here? If you draw the magnitude response, HD theta, only the magnitude, and the magnitude of that is 1. E to the power minus j3 theta, if you take the magnitude of that is 1. So it's pi over 4, 3 pi over 4, pi over 4, 3 pi over 4 is there, and pi is here, pi over 4, 3 pi over 4, and it is 1. And similarly, it's a modulus, therefore you have here also minus pi over 4, 3 pi over 4 minus, and it goes to minus pi. So that's your band pass filter. Having said that, if you take this one, HD theta, don't forget HD theta is equal to e to the minus j3 theta. Therefore, magnitude of HD theta is equal to 1, but the phase angle is equal to minus 3 theta. So this is a linear phase, don't forget that. Linear phase filter, this is. The one that's given to you is a linear phase filter. Anyway, the first part of it is find the impulse response. So we take inverse discrete time for your series. In your notes is there, and you say 1 over 2 pi, go from minus pi to 2 pi, substitute this one and e to the j and theta and integrate. When you do the integration, you will go from that to that and that to that. That's all. You don't need to go minus pi to, you will go from minus pi to plus pi, but these are all zeros, so you don't need to integrate. So integral changes to minus 3 pi 4 to minus pi over 4. H theta is equal to e to the minus j theta, e to the 3 theta, multiply by that is you add them together, so that's what you get. And then similarly you go for pi over 4 to 3 pi over 4 and you get that one. So once you have got this, all the integration part, now you've got to manipulate that in a particular way, what you want, right? So let's look at that part. Yeah? I need a bit more space here to explain that further. Okay, so we found some space now, right? So if you integrate that one, e to the j and theta divided by j in minus 3, and then similarly this one, when you do the integration, now you substitute these values and you'll get this one minus that, and then that one minus that. Now if you divide them, all of them by 2j, so if you take this one and divide by 2j, this 2j there comes underneath as 2j, it will become as a sine, and this also becomes as a sine with this, and you're going to switch them around to get the minus sign here. And the 1 over pi in 3 will be in the front. Now the thing is that you need to find the value when n equal to 3. You can't use this n equal to 3. You can't just directly substitute, it wouldn't work. So you use L'Hospital's to find, or you could go and say that sine n minus 3 pi over 4 divided by n minus 3, right? So sine, that is, you can say sine theta is approximately equal to theta when theta is small. Same thing, if you think this as a theta and this is theta, so this part goes then. So that and that cancel out, you get 3 pi over 4 for that, and that's for this part. And then if you, this part, and if you do this one here, the same format, sine n minus 3 pi over 4 over n minus 3, and using that principle, that's gone, so that and that cancel, you get minus pi over 4. And if you simplify this one, this will be 2 pi over 4, which is equal to pi over 2, and you already have a pi in the front, pi in the bottom, so that pi and pi cancels, you get half. That's one way of doing it to find the value. Anyway, that's the impulse response, first part. You have got that. The second part, if you look at it, they want you to compute the coefficients. So we got the impulse response of the band pass filter. The window for the impulse response, say assume the impulse response was, something like that, negative and positive, and right? Just arbitrary there. You got to plot the sine part, and you apply the window. So you can apply the window, a Bartlett window, and it's given to you. So first you calculate the window value at 0, 1 by substituting here, and 2, 3, 4, 5, 6, because you have the window length is 7. You calculate the window, and then you calculate from your previous one, from here, this is the HN. You find H0 is that, then H1 you substitute, H2, H3, H4 you substitute in here, and if you do that, you will have H node equal to whatever HT node we calculate, which is half times WB0, which is 0, so the output is 0. You find H1, substitute 1 in the previous equation, WB1 is 1/3, so you get that one, and you keep doing that one. You finish up to you need up 7 altogether. But remember that it's a linear phase filter, and linear phase filter, the beta we found as minus 3 theta, right? So when you calculate it, sorry, that's the phi theta, not beta, phi theta, and the beta is 3. That means the beta is normally calculated as n minus 1 over 2. N is 7 minus 1 over 2, which is 3. So what you really need to do is you calculate the first 3 coefficients. That's 1, 2, 3, and this is the fourth one at n equal to 3. It's a linear phase filter, so you just map that one there, it's symmetrical, this one there, and that one in there. So your coefficients are symmetrical around 3. That's all you need to know. So always for a linear phase filter, you must calculate the symmetry position, which is n minus 1 over 2. As soon as they say linear phase filter, you know the coefficients are going to be symmetrical. And where do you get the position? The center position, the symmetry position is n minus 1 divided by 2. Okay? So beta equal to n minus 1 divided by 2, 7 minus 1 over 2, which is what we have. So that's the coefficients for that particular linear phase filter. Now, this another question that you have is a digital filter you are going to design, and the digital low pass filter meets this specification. So you know is something like that. That's a theta axis, actually is a digital filter, and it is 0 to 10 kilohertz. You're going to convert them into, that's the theta c, and then sampling frequency is given. Fs is equal to 100 kilohertz and kilohertz, and the transition band is 10 kilohertz to 20, and that's one that part, this minus 3 dB, is this position is minus 10 dB. It's all given to you. So the first part for us is to convert all these analog frequency into theta. So theta c, cutoff frequency, 2 pi fc over fs, and you got 0.2 pi. Theta h we call it, so this is theta h, or theta s is also right. Theta h is equal to 2 pi fh over fs, which is 0.5. So once we have got that, we need to now go and do the pre-warping, because as I explained before. So how do you pre-warp it? This is the equation. So omega c we are trying to calculate. What's the analog frequency? Omega c, the new frequency that we need to do, such that when you do the warping, it will come as 10 kilohertz. It's 2 over t, 0.2 here, substitute, and it works out to be that. And similarly, theta h, you do the same thing for that as well, which is 2fs is, well, 2 over t is known as 2fs. That's still correct. Tan this is 0.4 pi, so it is theta over 2, so that if 0.4 pi divided by 2 will give you 0.2 pi, and you calculate them, that's what you get. We just call them that the attenuation is at 10 dB, at least 10 dB attenuation. And we can call this one as, I don't know why we call it omega s, but you can, because this is stop band, we could have used that from the start as omega s, but it was given as fh in the question, therefore we used as fh and we put as omega h, we changed them to omega s, showing that's a stop band. Okay? That's your pre-warping you've done. Now you're going to find the order of the filter. You don't know what order is the filter is, so you go. Now you go, right, this is our Butterworth equation. We know this value, we know this value, we know this value, minus 10 dB when you take the log on both sides. It's chapter 7 you have done, and that's where everything is explained here for that. From here, by substituting the appropriate values, you can calculate 2n, which become 1.37. Therefore, we choose n equal to 2. N is second order filter. Second order filter is very easy to find the pole position, which we have done previously. It will be 3 pi over 4 from here, and that's one is, right? And there are two positions you will have for the second order filter. And the pole positions are, first position is at that, it's that one, and the second one is that one, right? Or you could go this way pi over 4, that way pi over 4 as well, which you have done already. This is, And you find the pole position from chapter 7, which is that bit, which is that and that distance, and that's pi over 4. And then you can use this or pi over 4, minus pi over 4 as well, or that one, that is that distance and that one. Okay, so you got that pole positions, and now you write the transfer function, which is hs is equal to hs's transfer function is equal to, in this case, we could have written as 1 over sp1 times s minus p2. We could have written that way. But what we want to make sure at DC we want the gain to be equal to 1. So what we need to, when s is equal to j omega, then omega equals 0, what happens is, this is 0, you get P1, P2 underneath, 1 over P1, P2. So if you put P1, P2 on the top, then the gain will be 1. So that's why we have got the P1, P2 on the top. Okay? Now you substitute the value for P1, P2. You substitute for P1, you calculated it. P2, you calculated. You ended up a filter like that. Now once you have that filter, all you need to do is to do the bilinear transformation. This is 2 over t, right? Once you do the bilinear transformation, which you substitute here, you substitute there. That's all. And simplify them, you get that equation. I didn't show the simplification here, which is a simple algebra that you can do. Okay, now this is the last question in this paper, in this chapter. You've got a transfer function given hs, which is equal to alpha os plus alpha. And this is alpha actually, it's not a. Yeah? That's alpha. Alpha is given 10 to the 4. Sampling period is 100 microsecond. You have been asked to find, first part is, show that the transfer function h set. So starting with the analog filter, we have to show the transfer function is the one after doing bilinear transformation. And where a is given by 2 minus alpha t or 2 plus alpha t. So let's start with that. Before pre-warping, without doing any pre-warping, we say cutoff frequency time t is our thing. Cutoff frequency here is that omega c. So for a low pass filter, hs is equal to omega c over s plus omega c is your first order low pass filter. And instead of alpha equal to omega c, so we say omega c times t, which is alpha times t. T is given as 10 to the T is given as 100 microsecond. So if you multiply these two, you get 1. So you can say the sampling period is 1 over t, which is 10 kilohertz, right? Which we know. This got nothing to do with the sampling frequency from here. Theta c is 1. So we have to find the analog frequency. So we need to do pre-warping. Pre-warping is alpha, the new alpha. Or we can call alpha dash if you want. 2 over t, tan theta over 2, tan theta over 2. Theta is 1 here, that's 1, theta over 2. So you get your new alpha. So what's our required transfer function is going to be? Required digital transfer function is going to be h set. Hs, you substitute this one. And you need to have the new alpha dash there rather than alpha. Well, because the answer has alpha, we call it as alpha. It doesn't matter. This is the warped alpha. So we can keep it as alpha. That's because it's in line with. So I substitute that one there, and then I simplify. H set is equal to alpha t. So you multiply. Alpha t over 2, that's easy enough for you to do. That's this, because as soon as you substitute this t comes in and that 2 comes in on the top. So alpha t over 2 and that one. And you simplify this further, you get that one because you cross multiply that, you cross multiply this and bring this up and everything. And then you get that part. And we want to make sure this part is 1. So you divide everything by that up and down. So when you do that one, you'll get that and that coefficient. And we know this is being given as A. That's A. So you can substitute for A there. And if we simplify, we can show that that's A. 1 minus A over 2. So from here, if you take 1 minus A over 2, it will come as that. So we know this can be replaced by that. So now your equation become, this become 1 minus A over 2, that will be still there, and that will be there, this become A. So you go back here, that's your transfer function. We could have left it like that, but they wanted you to show this. So you go from that further, and you keep one, you bring this down as that, and divide by that, you get that and that. That's your answer. But that can be rewritten in this form, because these are same order, you can divide them. So you simply can write this, or when you cross multiply and add them, you'll get this one. So that's your answer for the first part of it. You've got your transfer function. Now move on to the next part. This is the last part of it. First you're going to, what is the DC gain at H set? That's the first part they're asking. So how do you find the DC gain? First you're going to calculate A. How do you calculate A or alpha? We know A is 2 minus alpha t. And you substitute values for alpha. Alpha we already calculated earlier, we know t. you substitute all of them here and you get 1/3. And also, you know, 1 minus a over 2 we need, which is 4 over 1/3 as well. So we now go and put into your transfer function. This is 1/3. That's your transfer function from the previous page. So 1/3, and then 1 plus a, which is 4/3. Then a is 1/3, and you got your transfer function. At that point, you can find h0, which is a DC. That's by setting that one, you'll get the answer. Or you can go h theta and then substitute theta equals 0. You can do it here or here. And when you find the DC gain become 1. Then at what frequency h theta equals 0? We know this is a low pass filter and the DC gain is 1. Right? So naturally you can try a pi there. So at pi, you substitute into this equation. You will find when you simplify them, that becomes 0. So at pi, the frequency is 0. Okay, now the third part is calculate the impulse response Hn. So how do you calculate the impulse response? We know the transfer function. We take the inverse of it. That's Hn equal to, nothing happened to that. That's still there. This will be delta n. We have delta n. And this is this part. If you have got 1 over 1 minus a set to the minus 1, that will be a to the n. Now because you've got a delay there, it will become as 1 plus a, that's the coefficient, time a n minus 1, and then this is un. So because of the delays, un minus 1. So that's your inverse transform. The next question is, assuming that the impulse response decay, so they're saying your impulse response decays it, like that, and to 1 over e of initial value. So initial value, whatever value, initial value you calculate, which is h naught times, h naught times, and 1 over e at n equal to n. So at n equal to n, you find out this value. This value is now going to be 1 over e times h0. Okay? So we now found that n is equal to, we are going to show that, right? So how do you do that? So you start with the impulse function. Impulse is here. So what impulses impulse response you've already calculated. So you substitute n equals 0 because we are trying to find the h0. h0 is 1 minus a. Delta 0 is 1. And this is like u minus 1. That would be 0. So that's gone. So this is equal to 1. So you get 1 minus a over 2. So h0 at that position equal to 1 minus a over 2. That's your impulse response. The next part, it says at n equal to n, you substitute hn equal to 1 minus a over delta n, that times that. Delta n will be 0 because delta 0 is 1. Here this will be equal to 1. So you will end up with that 1 minus a over 2 times that 1 plus a n minus 1. That's your equation 1. That is your hn. We know, according to the question, hn, that is that value hn, is equal to 1 over e times h naught. 1 over times h naught. H naught, 1 over e times, h naught is 1 minus a over 2, we calculated. So you know that this equation, 2 and the 1 are exactly same. So they're saying hn is 1 over e times of initial value. Hn is also calculated this way. You equate them, both of them. Now once you equate them, you find that you can cancel that one with that one, gone. So 1 over e is equal to 1 plus a, right, over a to the n minus 1, you can write as a to the n over a. So that's what you have written here. So that's first part. Then you take log on both sides because we want capital N. So you take log on both sides, ln 1 over e, ln 1 over e here. So if you do the log on both sides, you get, sorry, just we go back and come back, yeah. You got ln 1 over e, ln of that, plus, because log a, b is log a plus b, so plus, this will be log a to the n, a to the capital N comes in the front, so that's that one. So we are only after this now. So you move this one to this side, it will become minus. So n log a is equal to minus of that plus this one. This can be switched around. That goes up, that comes down. Then this sign goes plus. Right? And you combine these two. When you combine those two, this is what you'll get. Yeah. Because this will be ln1 is 0, ln e is equal to minus 1. Right? So if anybody don't know, you can do this one. ln1 minus ln e. ln1 is 0 minus 1. That would be ln e is 1. So that's what the minus 1 you have. So we know this is equal to that. Then from that you can say n equal to that part divided by this part. That's your answer. So if you track it how I have done, I mean there's a lot of scribble there, but if you track the way I've done it, you should have no problem. This is just simple log principle. Well, that's all you have now at the moment, like, you know. And if you look at the next one, there's nothing there. So that's all. That's the chapter 8 moral answers for you. Okay, just go through them again, redo the questions, and see whether you are able to do it within the time. Okay, thank you.